everyone, we are Group 7 and our project topic is RGB-D Vision. So to start off, you're probably wondering, what is that, right? You're most likely recognizing the RGB, so the red, green, blue, but then there's a D tacked onto there and you're probably wondering what that stands for. So basically that stands for depth. And depth is essential to this type of imaging because it not only includes typical color information, but it also includes, as I mentioned, depth. And these sensors use a camera to detect the distances the objects are from the sensor, and then that gives it the depth information. So what can they do? They can be used for object detection, pose estimation, virtual tracking, which on this side there are two photos, and the photo to the left is the one with the images themselves, and then to the right is the visual tracking and the depth information. And then they also can be used for shape analysis and 3D reconstruction. So basically, if you have images, you can use them to recreate a 3D model from the data that you already have that you've collected with these sensors. Now, what are the advantages to these sensors? So these sensors provide clear edges to the images because you can tell where the end of the object is. It's very clear. It's not the most high quality images, which will be next slide where I talk more into that, but sensors do give you a really good idea of the distance something is, as a depth sensor you'd imagine would do, but it does give a good idea of how far something is and where the edge would, because that just naturally comes with depth, right? So the viewer also can tell where the negative space is, which is important to note, because if you have an object and you can see it, that means that there is nothing in between that object and your eye. So for example, let's say that you have an object 5 feet away from you. If you can see that object, there is 5 feet of space between that object and your eye. So that means that there is 5 feet of implied space between those two. And that's what these cameras can depict because they are depth sensors. So on to the disadvantages. Like I mentioned last slide a little bit, there is a limited quality with these images because of the way they work, and I'll touch on to how they work later in the future, but the quality of the images aren't that great. They tend to be very pixelated, and there are ways to get around it. There are people who are creating ways to create higher quality images, but even these higher quality images aren't the best as far as quality is concerned. There's generally a lot of noise with these images. And there's also quantization, which we did learn in class, but if you want a refresher on it, it's basically when your data gets truncated or rounded, so that causes a reduction of quality. These images also struggle with if there are multiple objects near each other, since the quality isn't the best and they don't get the most specific as far as distance is concerned. Obviously, if you have two different objects far away from each other, it will do a good job at depicting which is which. However, if you have a lot of smaller objects that don't really have that many defined edges, it can make it hard for the camera to pick up on this. Which, as you can see in the rightermost photo, you can tell that the objects on the desk, you can't really make out which is which and what they all are, but you can tell the monitor and that there definitely is a monitor there and a little bit of the keyboard, but the keyboard you still can't really make out, and you definitely would not know that that was a keyboard had you have not recognized that there's a monitor there. Now, more connecting to in class, we also talked about stereopsis, which basically just is a difference in the eye angles, which is why we can tell how far something is, because both of our eyes have a different perspective, and then our brain takes that information and uses it to figure out how far away something is from another object. So an example of when we would use this is, let's say you're playing ball with someone and you need to be able to tell how far that ball is from you so then you can catch it on time. So both of your eyes are watching this ball get closer, and they both have a different perspective. So when that ball gets closer, each eye relays that information to the brain, and the brain figures out how far that is from you, and then you can catch it. Now, something that's very similar to this is the stereoscopic pair. So that is overlapping two images to create depth. And I'll talk about this in two sides, but basically it is creating an image to make it look like that there's depth. So when you were younger, you probably had those 3D glasses where there was one side that was red and another side that was blue, and then you would look through those glasses. And on the paper, without the glasses, there were two images that kind of overlapped, but you could still see an outline of part of it was red and another part of it was blue. And then when you put the glasses on, it looked 3D. And that's because of the stereoscopic pair, which is overlapping these two images to create depth. And like I mentioned, we'll talk about this in 2 more slides. But this idea is definitely not a new idea. There also is motion parallax, which to the right you'll see a photo of. This is basically an explanation of what it looks like. So I'm sure as you've been walking by, you've noticed that a tree will move faster than maybe a mountain in the distance. And that is a perfect depiction of motion parallax. So in the photo, you'll see from viewpoint A, that object would appear on the blue square. But if you are at viewpoint B, it would appear on the red square. And that basically is just that depending on your viewpoint, closer objects cover up different parts of the background. Which these concepts are very important for 3D reconstruction, which is what I mentioned earlier, where you combine a bunch of different images and create a 3D model. And so this is very important for that idea. Now, are there any circumstances where depth perception is used in nature? And there is. So like I mentioned before, where a brain figures out depth. And eagles also have this, where they have some of the best depth perception in nature, and they can see about 8 times as far as humans can. And they have a wider range of colors. They can see UV light, which they can see more differences in their environment. And even some animals like snakes, they can detect infrared light in their environment, and this works out really well for them because they can see in the dark because of that. So now on to early depth imaging. So where did this go? So Charles Wheatstone's stereoscope, like I mentioned, stereoscopic pairs when you overlap 2 images to create depth. So he did that in the Victorian era, where he used mirrors and photos to create this device, and it's called the stereoscope, which is basically stereoscopic pairs, and you look through it and it makes it look like that those photos now have depth because your eyes and your brain have a different view of each image. So now that we have it, what can we use this technology for? So we have Face ID, which the camera can recognize the shape of our face because of this type of vision. Now, the way that it works is there are these little dots, and the way that I think of it is they're like constellations. So each little cluster of dots is all unique in the pattern that they have. And so these dots are projected, creating this unique infrared pattern, which we can't tell. We can't see that with our own eyes. And after these dots are projected, they are then read by a sensor, and that sensor takes that data and triangulates it to figure out how far away the object is. Now, since this technology uses infrared, it can't be used in the sunlight, so it has to be done indoors. Also, the way that it can tell movements is because it compares the changes in depth so that it knows where the movement is occurring. Now, the last thing I'd like to highlight is that the projections, you can tell that they're little dots, and this is why the image isn't the highest quality, because it's projecting dots, and these dots can have a tendency to, one, reflect, and there can be light from other sources, creating this kind of effect that messes with the sensor. And so sometimes that'll reduce the quality of the image. And it also, the dots, if you picture them as kind of like pixels, it'll be very pixelated if there aren't that many of those dots. And there aren't, because the dots have to be a distance away from each other. And so this creates kind of a little bit of a pixelated image, as well as, like I mentioned before, with the issues of the light refracting across the room and other issues like that. Overall, this technology is definitely still emerging, and they're still working to refine it and make it much better than what it is. But this is where we're at right now, technology-wise, and maybe one day you can decide to help and make this better.